All right, let's go. Number 7, the cosmic size paradox. The paradox begins with a number that should never have matched. In classical general relativity, a black hole forms when a mass is compressed inside its Schwarzschild radius. That radius defines a boundary beyond which escape is impossible, not because gravity pulls harder, but because spacetime itself tilts inward faster than light can move outward. The formula is simple. The implication is not. If you take the total mass energy of the observable universe and calculate the Schwarzschild radius associated with it, you get a value that is uncomfortably close to the observed size of a universe itself. Not similar in scale, not roughly comparable, within an order of magnitude. This coincidence was noted decades ago and refined as cosmological measurements improved. The radius of the observable universe, defined by how far light has traveled since the beginning of cosmic expansion, is on the same scale as the gravitational radius expected if that mass energy were contained in a single spacetime region. This was not predicted. It emerged. At the largest scale, the universe behaves as if it is balanced precisely on the threshold between expansion and gravitational containment. Galaxies recede from one another, yet the global curvature of spacetime remains nearly flat. That flatness is not trivial. It requires extreme fine-tuning in the early universe, or an underlying geometric constraint. Move down one level, to galaxy clusters. They are bound systems embedded in an expanding background, held together by gravity while space stretches around them. The same duality appears again. Local collapse inside global expansion. Stars form by gravitational contraction inside galaxies that themselves ride an expanding metric. Planetary systems condense from disks that shed angular momentum irreversibly, locking matter into tighter orbits. Every step downward involves loss. Energy radiates away. Entropy increases. Structures form by falling inward, never outward. At the atomic scale, binding energies dominate. Particles drop into lower energy states and emit photons that will never return to recreate the original configuration. At the quantum level, vacuum fluctuations briefly borrow energy, but must repay it within strict limits. Irreversibility persists. Now introduce time. In black hole physics, time does not end at the horizon. It changes role. Inside, the radial direction becomes time-like. Moving inward is as unavoidable as moving toward the future. There is no static interior. There is only progression. Cosmological time behaves similarly. The universe does not evolve toward equilibrium from our perspective. It evolves away from a low-entropy past. The arrow of time points in one direction because it cannot point in any other. Reversal is not forbidden by equations, but by boundary conditions that can never be reestablished. The unsettling part is this. If the universe were inside a black hole, its expansion would not contradict that fact. From the inside, expansion is expected. The interior geometry of a black hole is dynamic. Space grows as even escape becomes impossible. The paradox is not that the universe looks like a black hole. The paradox is that mathematically, it does not seem allowed to look like anything else. This connection was first explored rigorously in solutions to Einstein's equations by physicists such as Carl Schwarzschild, whose work revealed that horizons are not objects in space, but properties of spacetime itself. Once such a geometry exists, no internal measurement can reveal the exterior. If we are inside, there would be no signal announcing it. Only coincidences that refuse to go away.
Number 6. The horizon without an edge. A black hole is defined by an event horizon, a boundary beyond which information cannot return. It is not a wall. It is not a surface. It is a limit imposed by space-time geometry itself. From far away, it appears frozen. From nearby, it does not appear at all. And from the inside, it ceases to be meaningful as a boundary in space. It becomes a boundary in time. Now consider the observable universe. There exists a horizon beyond which we cannot see. Light from regions farther away has not had enough time to reach us since cosmic expansion began. This is not due to technological limits. It is a fundamental constraint. No signal, no matter how advanced, can bypass it. Information beyond this boundary is causally disconnected from us forever. That alone is not strange. What is strange is how similar this cosmic horizon is to a black hole horizon in every operational sense. At the largest scale, galaxies recede from us faster as distance increases, not because they move through space, but because space itself expands between us. At a critical distance, that expansion exceeds the speed of light. Beyond that, causal contact is permanently lost. This is not a violation of relativity. It is a geometric inevitability. In black hole physics, the same inevitability appears. At the event horizon, the outward flow of spacetime equals the maximum speed allowed for information. Beyond it, outward motion is no longer a meaningful option. All future-directed paths point inward. Scale down. Within galaxy clusters, horizons emerge in subtler forms. Gravitational wells trap hot gas for billions of years. Escape velocities define regions of no return for particles that lack sufficient energy. Stars form cores where fusion ignites, and beyond certain radii, matter can never escape the inward pull without additional energy input. On the scale of planets, atmospheres retain masses until thermal escape thresholds are crossed. Once lighter molecules drift away, the loss is irreversible on geological timescales. Mars did not choose to lose its atmosphere. It crossed a boundary condition and could never return. At the atomic level, electrons occupy quantized states. When one drops to a lower energy level, the emitted photon leaves. Reconstructing the original state requires an exact reversal of conditions that almost never occurs. Information leaks outward, never inward. At the quantum field level, horizons produce real physical effects. An accelerating observer perceives a warm bath of particles where an inertial observer sees none. This is not metaphorical, it is measurable in principle. Horizons change what exists. The paradox sharpens here. Horizons are observer-dependent, yet their consequences are absolute. Entropy increases, information becomes inaccessible, physical processes become irreversible. If the universe is inside a black hole, its cosmological horizon is not an outer edge. It is the interior equivalent of an event horizon. We do not see it because we are embedded within it. We experience it as the finite size of our observable universe and the one-way flow of cosmic time. The most destabilizing aspect is this. A black hole horizon does not require a singularity nearby to function. It only requires global geometry. Likewise, the universe's horizon does not announce an exterior. It only enforces limits on what can ever be known. There is no edge to point at, only a boundary that recedes as we approach it, forever defining what the universe allows us to experience.
Number 5, the entropy reversal problem. Entropy is not just a bookkeeping tool. It is the reason the universe remembers its past but not its future. It is why broken things do not unbreak, why heat flows in one direction, and why time itself appears to have an arrow. In ordinary systems, entropy increases because there are more disordered states than ordered ones. This explanation works well for gases in boxes and stars burning fuel, but it quietly fails at the largest scale imaginable. The universe began in a state of extraordinarily low entropy. Not low temperature, hot, dense, energetic, but geometrically smooth. Matter was distributed with astonishing uniformity. Gravitational degrees of freedom were almost perfectly unexcited. This is the opposite of what probability predicts. Gravity prefers clumping. Left alone, matter collapses, structures form, entropy rises. A high entropy gravitational state is one filled with black holes. And yet, the early universe had none. This is not a philosophical discomfort, it is a quantitative paradox. If the universe were a closed system evolving forward in time, its initial conditions were improbably special to a degree that defies statistical explanation, unless the arrow of time did not originate there. In black hole physics, entropy behaves differently. A black hole's entropy is not proportional to its volume, but to the area of its horizon. This insight, developed through the work of physicists like Stephen Hawking, revealed that black holes are not entropy sinks. They are entropy maxima. Nothing you add decreases their entropy. Information is not destroyed, but it becomes inaccessible. Inside a black hole, entropy does not increase towards the singularity in the way it does in ordinary systems. Instead, the boundary conditions at the horizon define the arrow of time. The interior inherits its temporal direction from the horizon itself. Now apply this to a cosmology. If the universe is the interior of a black hole, then the low entropy beginning is not an unexplained miracle. It is a boundary condition imposed at horizon formation. Time inside begins not because entropy was chosen to be low, but because the geometry enforces a direction. As the universe expands, structure forms, galaxies condense, stars burn nuclear fuel irreversibly over billions of years, heavy elements accumulate, black holes form and merge, entropy rises monotonically exactly as expected inside a system evolving away from a boundary. At smaller scales, the same logic holds. Chemical reactions proceed toward equilibrium. Biological systems locally decrease entropy only by exporting greater entropy to their surroundings. Atomic nuclei fuse and decay on fixed timescales. None of these processes reverse spontaneously. The paradox is this: the universe looks like a system that began at a horizon, not a system that randomly started in a low entropy state. If true, the Big Bang was not the beginning of everything. It was the interior boundary condition of a spacetime region whose entropy budget was already maximized from an external perspective. From the inside, we experience this as time flowing forward. From the outside, if such a perspective exists at all, nothing unusual happened.
Number 4, the singularity that acts like a past. In every black hole solution of general relativity, there is a singularity, not a place in space, but a breakdown of spacetime itself. Densities diverge, curvature becomes infinite, the equations stop making predictions. And most importantly, the singularity is not something you move towards spatially. It lies in your future. Once you cross a black hole's horizon, the singularity is as unavoidable as tomorrow. No force can prevent it. No path avoids it. It is not a destination you choose, but a temporal endpoint imposed by geometry. Now compare this to the Big Bang. The Big Bang is often described as an explosion in space, but this is wrong. It was not matter expanding into emptiness. It was space itself emerging from an initial condition where density and curvature diverged, like a singularity. And like a black hole singularity, it lies in the past of every observer. Every world line in the universe traces backward to the same boundary. No matter where you are or how you move, your past converges. You cannot avoid it. You cannot go around it. You cannot observe before it in any operational sense. This is already strange. But the deeper paradox appears when we examine causality. In black hole interiors, the singularity defines the direction of time. Physical processes do not lead toward it because of forces. They lead toward it because spacetime allows no alternative. Cause and effect align with geometry. In cosmology, time also flows away from the Big Bang, not because it must mathematically, but because entropy increases in that direction. The singularity defines the low entropy boundary condition from which all irreversible processes unfold. At the scale of cosmic structure, this is clear. Density fluctuations grow into galaxies over hundreds of millions of years. Stars ignite, evolve, and die on timescales of millions to billions of years. Heavy elements are forged in supernovae. None of these processes can be run backward without violating the second law of thermodynamics. At the planetary scale, geological processes erase their own past. Plate tectonics recycles crust. Radioactive decay marks time irreversibly. At the molecular level, chemical reactions proceed toward equilibrium. At the quantum level, measurements decohere states, permanently dispersing phase information into the environment. Every arrow points away from the Big Bang. Now consider a subtle but critical feature of black hole interiors. The singularity is not ahead in the same way space is ahead. It is not a location you can describe with coordinates independent of time. It is the termination of time. The Big Bang behaves the same way. It is not an event that happens somewhere. It is the limit of past time. Asking what came before it is like asking what lies south of the South Pole. This analogy was sharpened by work on spacetime singularities by physicists such as Roger Penrose, who showed that under very general conditions, singularities are unavoidable in both black holes and cosmology. The paradox is this: if black hole singularities lie in the future of their interiors, and the Big Bang lies in the past of our universe, then the universe's temporal structure mirrors that of a black hole turned inside out. Or viewed differently, our past may be another system's future. Number 3, the information that never leaves.
In physics, information is not abstract. It is physical. It is encoded in particle states, quantum correlations, and field configurations. And according to every fundamental law we trust, it cannot be destroyed. Black holes challenge this. When matter falls into a black hole, its detailed information appears to vanish from the observable universe. From the outside, only mass, charge, and angular momentum remain. Everything else is erased. For decades, this created one of the deepest crises in theoretical physics, the black hole information paradox. The resolution, as far as one exists, is subtle. Information is not destroyed. It is smeared across the event horizon, encoded in microscopic degrees of freedom that preserve unitarity. But once inside, that information can never return in usable form. It still exists. It is simply inaccessible. Now apply this logic to the universe. The universe has a finite information capacity. This is not speculative. It follows from combining quantum mechanics, gravity, and thermodynamics. There is a maximum amount of information that can be stored within a region of spacetime, proportional not to its volume, but to the area of its boundary. This is known as holographic behavior, and it is exactly how black holes work. At the largest scale, the cosmic horizon limits the information available to any observer. No matter how long you wait, signals from beyond a certain boundary will never arrive. The universe may be vastly larger than what we see, but its information is causally sealed off. At the scale of galaxies, information is lost in mergers. When two galaxies collide, detailed orbital histories of individual stars are scrambled beyond recovery. The system relaxes into a new equilibrium. Entropy rises, information disperses. In stars, nuclear fusion converts mass into energy. The precise quantum states of the original particles are unrecoverable. In planets, erosion erases surface records. In atoms, spontaneous emission releases photons whose phase information disperses into the environment. In quantum systems, decoherence spreads information into correlations that can never be recombined. Everywhere, information flows outward, never inward. The paradox emerges when we ask, where is the information about the universe's initial state now? If information is conserved, it must still exist, but it is not locally accessible. It is encoded globally, distributed across the largest possible boundary, the cosmic horizon itself. This is exactly what happens in a black hole. The information about everything that has ever fallen in is not inside in any ordinary sense. It is stored on the horizon, inaccessible to interior observers, yet preserved in principle. From inside the universe, we cannot access the information that defines the full state of the cosmos. We only ever see a projection, a low-resolution slice consistent with our horizon. The unsettling implication is that the universe behaves like a system whose information ledger is kept at a boundary we cannot reach, not because of technological limits, but because of geometry. Number 2, the expansion that looks like falling. At first glance, cosmic expansion and gravitational collapse appear to be opposites. One spreads matter apart, the other pulls it inward. One suggests freedom, the other imprisonment. But in general relativity, those intuitions are unreliable. In the equations that govern spacetime, expansion and collapse are not distinct processes. They are different coordinate descriptions of the same underlying geometry. What matters is not whether distances increase or decrease, but how spacetime itself evolves. Inside a black hole, space expands. This is not a metaphor. Once past the event horizon, the radial direction becomes time-like. Distances between points grow inevitably in the direction of the singularity. Matter is not being pulled inward through space. Space itself is stretching in a way that carries matter along. From the inside, the black hole does not feel like collapse. It feels like expansion toward an unavoidable future. Now compare that to cosmology. The universe is expanding. Galaxies recede from one another. Light is redshifted. Distances increase over time. But this expansion is not motion through space. It is the growth of space itself. Objects at rest with respect to the cosmic frame are carried apart by geometry, not force. This similarity is not superficial. In black hole interiors, the expansion rate is determined by mass and curvature. In cosmology, the expansion rate is determined by energy density and curvature. The equations are formally related. Under certain coordinate transformations, the interior of a black hole can be rewritten to resemble a cosmological spacetime, complete with an initial singularity and expanding spatial slices. At the scale of galaxy formation, this duality becomes visible. Regions that are slightly denser than average decouple from expansion and collapse to form galaxies. Inside those regions, space effectively contracts while the universe at large expands. Both processes coexist without contradiction.
Within stars, gravitational contraction raises temperature until nuclear fusion ignites. Energy flows outward, mass energy converts irreversibly, and the star slowly changes structure over millions to billions of years. Collapse generates expansion of radiation. At the planetary scale, contraction during formation releases heat. Differentiation locks in irreversible structure. At the atomic scale, particles fall into bound states and emit energy that escapes. At the quantum scale, fields relax toward lower energy configurations, dispersing excess energy into spacetime. Everywhere, falling inward produces outward flow. The paradox is that cosmic expansion behaves less like an explosion and more like the interior evolution of a gravitationally bound system. The universe expands the way space expands inside a black hole, not away from a center, but forward in time. If this interpretation is correct, then what we call expansion is not escape from gravity, it is gravity expressed globally. From the inside, it feels like growth. From the outside, if an outside exists at all, it would look like collapse frozen at a horizon. And the most disturbing implication is this: accelerated expansion does not free us from that fate, it deepens it. Just as nothing outruns the interior geometry of a black hole, nothing outruns the universe's expansion-driven horizons. We are not moving away from something, we are moving forward into it.
Number 1. The vacuum that defines reality. The final paradox does not live in stars or horizons or geometry alone. It lives in the vacuum itself. In everyday language, vacuum means empty. In physics, it means the lowest energy state of all quantum fields. And that lowest state is not stable in the way common sense expects. It is dynamic, fluctuating, and defined by boundary conditions imposed by spacetime. In quantum field theory, particles are excitations of fields that exist everywhere. Even in perfect emptiness, these fields fluctuate. Virtual particles appear and disappear. Energy briefly violates classical constraints, then settles back down. This is not noise layered onto reality. This is reality. Now introduce gravity. Gravity does not merely respond to matter, it responds to energy, including vacuum energy, and vacuum energy curves spacetime. Here is the destabilizing fact. The vacuum state inside a black hole is not the same as the vacuum state outside it. Horizons change what nothing means. An observer near a horizon experiences particle radiation where another observer sees none. Temperature emerges from geometry alone. This implies something profound. The vacuum is not absolute. It is contextual. Now apply this to the universe. The universe has a vacuum state. That vacuum has energy. We measure it indirectly as dark energy, the driver of accelerated cosmic expansion. Its value is small, positive, and stubbornly constant across space and time. But there is no known principle that fixes this value. Quantum field theory predicts vacuum energies that are catastrophically larger. The observed value is not just small, it is tuned to an absurd degree. Unless it is not chosen, unless it is imposed. In black hole physics, the horizon defines the allowed vacuum structure inside. Field modes are truncated, information is restricted. Energetic configurations that would exist in unbounded space simply do not appear. The vacuum adapts to the geometry. If the universe is inside a black hole, then its vacuum is not fundamental, it is inherited. The constants we treat as bedrock, the speed of light, the strength of forces, the mass of particles, may not be arbitrary. They may be the only values consistent with a self-contained interior spacetime bounded by a horizon. At the largest scale, vacuum energy drives expansion, which defines the cosmic horizon. That horizon defines which field modes exist. Those modes define particle behavior. Particle behavior defines chemistry. Chemistry defines stars. Stars define time. At the atomic scale, vacuum fluctuations shift energy levels. At the subatomic scale, they renormalize masses. At the spacetime level, they determine whether expansion accelerates or stalls. This is not circular reasoning. It is a closed system. The paradox is this: the deepest properties of reality may not originate within the universe at all. They may be boundary conditions enforced by a horizon we can never observe. If so, then the fabric of reality is not self-contained. It is consistent, not because it must be, but because it is allowed to exist at all.
If this is true, then our place in the universe changes, but not in the way science fiction imagines. We are not trapped in a prison of gravity. We are not doomed by hidden walls. We are participants in an interior spacetime that has enough room for galaxies, chemistry, life, and thought to arise before its ultimate limits are ever felt. On human timescales, the universe is effectively infinite. Civilizations rise and fall, species evolve, stars are born and die. None of this is threatened by horizons that exist tens of billions of light years away or singularities buried in an unreachable past. What changes is perspective. If the universe is inside a black hole, then our cosmic era is not generic. It is early, structured, temporarily far from equilibrium. Stars still burn, heavy elements still form, complexity is still possible. That will not always be true. In the far future, expansion will thin matter beyond usefulness. Black holes will evaporate, structures will fade. The universe will approach a state where change becomes rare. But that is not now. Now is a narrow window where geometry allows chemistry, where entropy gradients allow memory, and where minds can form models of the universe that contains them. Whether or not we are inside a black hole, the lesson is the same. The universe does not owe us permanence. It offers us coherence for a while. And within that coherence, we get to look outward, measure the limits of knowledge, and realize that even if we can never see beyond the horizon, the fact that we can see anything at all is extraordinary.